think we should be able to get started then.
Okay, so shall I share my screen, or is Hamid how to?
I think you guys, either of you guys, have to share your screen.
Okay.
Yeah.
Good.
So just to make it official, this is the presentation title is Uber Universal 48-volt Power Shelf.
Yep.
By Ming and Harry from Uber and Artisan respectively.
Yeah. Can you see my screen?
Yes, I can see your screen.
It's the slide, right?
Yeah, you can go ahead and present with the present button.
So how about now? Is it presentation mode?
Yes, looks very good. Go ahead.
Okay. Okay. Shall we start now?
Yes.
Okay. Good afternoon, everybody. My name is Mingchen Xu from the Uber hardware team. Today, the presentation is for the Uber 48-volt Power Shelf. There will be the three speakers: Carson from Delta, Germany, the Harry from the Artisan, and me. Our agenda is I will do some introduction for Uber data center power infrastructure and give some the key specification of the power shelf and the power supply and the Delta Carson will do the simple that the power shelf the specification introduction and focus on the impedance design. Harry will introduce the Artisan power shelf and the focus on the EE mechanical and the thermal design. Everybody know that the Uber is the largest the company for the rideshare and the food delivery, and a lot of data is being processed every day for every trip and the every delivery in the Uber data centers. The power delivery is very critical, for the rack and the power, to keep that the server running the high efficiency and the higher the reliability. This is that I give the just quickly that the power pass for the Uber data centers. As others, the Uber also uses three-phase transformer to convert the medium voltage to the low voltage to the data center building. And we do use that the traditional the centralized the UPS to add the backup. And follow that, we will have we will deploy the PDU to further convert the voltage, lower down the voltage, and to provide the power to the rack through the busway. Since we use the UPS, central UPS, we have the dual AC. We have a dual AC source to the rack, for the power redundancy. This is the Uber 48-volt rack structures. The Uber's rack is a 19-inch EIA rack. As just now mentioned, we have the dual AC source. That dual AC source will lead into the rack through the CDUs. Each of the CDU, we have the two output, the connector to support the power to the power shelf, and one the AC the plug. For the we follow that the OCP standard, the 2.2 to design the rack bus bar to get the shelf power delivered to the server in the rack. This is the key, that's the spec for the Uber power shelf. The power shelf is 2 RU high with 960 millimeter depth. The count from the front panel of the power shelf to the edge of the bus bar. The maximum power is about, we designed for the 30 kilowatt with the 12 power supply slots. In this, the configuration, we can, do either 11+1, 8+1, 5+1, 2+1 to keep that three-phase balance and to accommodate the different the power requirement at the rack level. Just now mentioned about, we have the dual AC source. We can, the power shelf can work with either, the Y or delta connections. Delta the Y and delta the source from the grid, and also, please be noted here is 2 AC connectors in the from each source to power shelf. That will give the flexibility. So power shelf can be working either with either the higher amperage, the AC plug from the busway, or 2 small amperage AC plug from busway. That gives some the flexibility. And for the connection between the power shelf to the rack bus bar, we use the screw to tighten these 2 bus bars together to keep that lower contact resistance and save the power loss. The power shelf is this power shelf. I'm sorry. So power supply is 3 kilowatt for that the 48 power supply that jumped from the 50 volt to 48.5 volt from the 0% load to 100% load. It's AC universal AC input. Uber we use that the highlight only. We prefer 68 millimeter in order to put that 6 power supply in 1U into the that 19-inch rack. Since we we have a dual AC input, but we still want that save some that the efficiency and the keep that the not use N plus N redundant. We implement that the auto transfer switch into the power supply design. So efficiency we ask for 97% the peak efficiency. So the SMC can be put, the shelf manager controller, can be put either, the front, in the front of the power shelf, and also the rear panel of the power shelf. We just define that the SMC need to communicate to the rack switch through the Ethernet in Redfish command. As the function is very general. It's the metering, power metering, status monitoring, the power supply control, and the SMC power supply firmware upgrade. Also definitely that SMC is hot pluggable. When missing the SMC, it should not affect the power delivery to the rack. It's only affect communication. I will hand over to Carson for his slides.
Yes, thank you, Ming. Can you hear me, everyone?
Yeah, go ahead.
Yeah, very well. So thank you. I'm going to present now the data approach for the Uber power shelf design and the power supply design, and I want to emphasize how we are using these advanced methods for the power supply impedance characterization in order to look for the data center stability performance. So my outline is I will give you a brief introduction of the shelf specification and the Uber power supply. Then I will go over to the impedance stability criteria. Then later on I will show how we are measuring and modeling the impedance of a power supply. And I want to show you some showcases where we see the impact of grid impedance on the power supply performance. And I will end my presentation with a summary. So our power supply is, as like Ming was already saying, the specification showing here on the right hand side, mainly saying it's with an ATS, so an automatic transfer switch. And from engineering point of view, what's some kind of tricky is the high requirement for a lot of hold up time. So 30 milliseconds means that we have to install a lot of bulk caps and make some tricky things to increase the hold up time. The specification of the power shelf on the next slide shows that we can plug 12 of these power supplies into the shelf, where we can install in total 30 kW power into the shelf, like required by the spec. The efficiency here is 97% peak efficiency, also due to the ATS functionality. Next, please. So now we come to the main point of this presentation that's related to the impedance stability modeling. So if you assume that the power supply is operating with a grid impedance like shown here in the top schematic, you will end up, when you do simple voltage divider calculations, that you have to look for the ratio between the impedance of the power supply and the impedance of the grid. And if you apply then the Nyquist criteria, you see you should never end up with the real part of this ratio in the complex numbers, that it should exceed the -1, because then the denominator becomes 0 and we have an unstable point. So this is basically saying the Nyquist criteria to prove the stability of the system. So how do we do that? The first thing is we need a definition of how we measure the impedance of the power supply. In our case, we do this by doing the input voltage perturbation method. So that means we have a small perturbation in series of the input voltage that gives an excitation of the voltage to the power supply, and we measure the response, which is in this case the current. And then we divide the voltage by the current and we get the impedance of the power supply. That is what we then call the small signal impedance. You can do this modeling by the equations, but I think we don't have to go into that much details here. Next, please. If you do that in this manner and you do a first measurement, you will end up with some graphs which look like on the right hand side. So the graphs show in the top one the impedance magnitude, and the lower one is the impedance phase. And I want to show you here some 3 showcases. The first one is what we call a fast sampled input voltage. So that means we are calculating the reference current out of the waveform of the input voltage. And this input voltage is now fast sampled. So in digital control, it's sampled every switching cycle. The next one is then in dark blue, the slow sampled V-in. So that means we are doing the same actually, but we do not do it cycle by cycle, but we use every second cycle for the measurement. And the last one, the bright blue one, is what we call the artificial sinusoidal waveform. That means we are synchronizing an artificial sinusoidal calculated waveform to the frequency of the grid and calculate the reference current out of that. If we do an interpretation of this these graphs, it's much more easy to use the blue one and the red one. Here we can identify that the phase starts roundabout at 100 degrees at a very low frequency. If you extend or extrapolate that waveform to 0, you can see that this is typically the constant power operation. If you increase the frequency and the phase sign changes, that means it comes from constant power operation back to 0 phase roundabout at 100 Hertz. Here we are operating in ohmic mode, so this is a purely ohmic resistive behavior. And then if we exceed, let's say, around about 1K Hertz, the phase shifts down to -90. This means it's a capacitive behavior, and this can be explained by the reason that no current or voltage control loop can follow anyhow the reference, and therefore only the EMI filter, which is typically capacitive, becomes valid here in that region. Okay, next one, please. We now combine this impedance measurements results with the impact of the grid impedance. In this case, we installed simply an inductance value of 640 microhenries, and we plot the Nyquist plot on the bottom right graph here. And we see that, for example, here the slow sampled V-in reference shows that we are operating very close to the point of -1. That means we would expect here an almost unstable behavior. And this is then shown in the waveforms on the next slide. So this means On the left-hand side, we have the in this graph we show the fast VN sampling. Here we had the largest gap to the point of -1 in the Nyquist plot, and this looks very stable. But on the right-hand side, we see that the slow input voltage sampling has some oscillations, also regarding to the Nyquist plot, and we see this here all the time. We are having a zero crossing. We have a significant oscillation in the input current. On the next slide, I have a second showcase. Here we installed an inductance value of 2.4 millihenries. And here we saw that the impedance with the artificial sinusoidal waveform reference current generation is the closest, gets the closest value to the unstable point. And in the waveforms on the next slide, you see again here the fast input voltage sampling is the most stable operating one, while the artificial sinusoidal waveforms shows huge oscillations all the time. We are having a zero crossing. So this gives me to the summary. So in as I was saying, in theory, unstable data center operation can be checked by the Nyquist criteria, as I have shown. I have shown you how we do the small signal modeling and how we are doing the small signal measurement in the power supply. I have done some reflections on the regions of operation, and I have shown you that the Nyquist criteria theory proves the stability of the power supply when operating with some grid inductances in two showcases. So, and we see that we can ensure the safe operation of the hyperscale data center by using this method. Okay, thank you very much. And now I will hand over to Harry.
Thank you, Carsten. Good afternoon, folks. My name is Harry Soin. I'm from Artisan Embedded Power, which is a division of Advanced Energy. I'm a senior technical marketing director responsible for the hyperscale space, and I'm located in San Jose, California. All right, so in this session, we will be talking about the new Uber Power Shelf. So here at Artisan, we are in the process of developing the new Power Shelf, which is very suitable for the standard EIA racks, which are 19-inch wide, and this can be easily adapted for 21-inch racks as well. This uses, as pointed out by Ming-Chun and Carsten, 68 millimeter power supplies, and the items on the right showcase the key items. All right, diving into the agenda, it's divided into 3 parts. I will be tackling the PSU design approach, followed by the PSU thermal simulations. And finally, we will be talking a bit about the shelf design approach. Thanks, Ming. So here, diving straight into the PSU specifications, the power supply has been optimized for 240 volts operation. It has a very challenging 97% peak efficiency, and that is that's a great number considering that the power supply has an ATS embedded in it. And as pointed out by Ming and Carsten, it has a very high hold-up time, which is onwards of 24 milliseconds. The PSU has built-in dual AC inputs with ATS. The output is 48.5 at full load, at 50 volts at no load, and has the usual protection circuitry. Moving on to the next slide. Thanks, Ming. So I'm really excited to showcase to you a very unique feature of this Artisan built power supply, that we have a detachable ATS module. So the PSU here, as you will see in this slide and the next slide, has a detachable ATS module and a control circuit. So for the PSUs, for the models or systems which require ATS, this could be embedded in it as you see on the pointer. Or for the version, if someone doesn't need the ATS, this could easily be detached and can be easily replaced by a bypass PCB, as you will see on the next slide. So making the implementation very, very simple. So this was a unique feature I wanted to talk about, because a lot of our customers do not require ATS and some of them do based on their application. So this is a unique feature which we wanted to point out, which was designed by Artisan. Next one, please, Ming. So after having covered the general PSU specifications, we will move on to the thermal simulation part and give you a little bit of the idea as to what work we have been doing on the thermal simulation front. So the next slide shows you the general guidelines for the thermal simulation, which we did. The thermal simulation has been done in the two key scenarios. There's a full load, both are full load, but there is a 208 volts nominal operation, as well as 180 volts, which is one of the stringent conditions. And we also keep in mind the ambient condition is 40 degrees C, 2000 meter altitude, and with the required back pressure. So all in all, as you see from the flow therm simulation here, it power supply looks like it's got a very good thermal margin at the right airflow, and it's well within the guidelines. So in the next slide, we will deep dive into the key parameters. Everybody is concerned, okay, so what are my key parameters at? What do the margin I have on my main transformer, the ATS relays, my power factor FETs, DC to DC FETs, and the sync FETs. So here, as you see, at 208 volts, at highest temperature and the highest altitude, the temperatures are well within the derating guidelines. These are not only artisan guidelines, but also the IPC guidelines. You will see, however, in the bottom simulation, the 180 volts runs a little bit hotter, but that is expected as the peak currents are almost always higher at the low line input. So that's the flow therm simulation. So moving on to the next slide, we will dive into the shelf design approach, which Artisan has adapted for this power shelf. So again, this is the 202 OU power shelf, which houses 12 PSUs, 3 kilowatts each, and it has front removable or a live insertable SMC controller, which is on the far right, as you will see from there, and it has 12 PSUs in the power shelf. Moving on to the next slide. I want to point out a unique feature of this artisan design where we use dual horizontal back planes with mezzanine type bus bars. As you see, these two unique bus bars allow for the airflow, to minimize the airflow impedance so that there could be maximum airflow. So that is a unique feature of this design. Plus, in addition, I want to point out, what Ming was pointed out earlier, is that the bus bars here are welded, and essentially that provides the lowest possible impedance. And one more feature is the bus bars are insulated with tubing when they exit the power shelf. So that is another key aspect of this power shelf and this unique design. Thanks, Ming. So moving on, we will talk a little bit about the shelf AC connection. And as you see, and as pointed out by Ming, you have the option of using either 2 AC input connectors or using 4 input connectors. And what I want to point out here is the AC connectors cannot be accidentally removed here, because you see this protective covering on top of that, and you shall require a plain screwdriver or a tool to remove them. So this is again a good safety feature which is inherent in this power shelf. Thank you, Ming. So moving on, just to highlight the shelf input connectors, so we can use either 2 input connectors, which are the Scorpion type a positronic connector, or you can use 1 connector. And the advantage of using 2 connector is, that the big challenge with this thing is, as we heard during the daytime, is, the bending radius because of the large currents. That is a very challenging aspect. And this design and this approach takes that stress out, and the bending radius, for the AC input whip can be minimized, right? And that is a great advantage of the shelf approach. Moving on to the next slide. So here we come to the final slides or final slides, and showing you how this beautiful shelf will be implemented into the rack. So you can see the 2 whips coming down from the top. You're seeing the bus bars, and you're seeing the power shelf, which is 770 millimeters wide from end to end for the EIA rack. And moving on finally to the shelf DC output bus bar connection. And again, we need to emphasize, here you're getting a complete view of the AC input connectors and the bus bars and exactly how the bolted joints and how this connection is implemented to get the minimum possible impedance and optimize the shelf design. So that pretty much completes the aspect of the artisan design PowerShelf. And I like to encourage the end users to follow or at least evaluate these specifications for their rack power design, as it has unique built-in really good features. And to move this forward, Delta and Artisan will work together and they contribute the product spec to the OCP community. So with that, I'll hand over to the panel, and we look forward to your questions.
Thank you for the great presentation. It was great to see the several companies work together for these products. A couple of questions I have before here. What's the communication? What was the communication? Was it Ethernet?
Yeah, yes, that. Yeah, from the PowerShelf to the switch is about Ethernet.
And what was the speed, data speed on that?
Yeah, this can be, that's the standard, the 10, the 100, the 1 gig, yeah.
Okay. All right. The other one that I saw was that, the voltage, seems like the voltage range that you are specifying is a fixed output voltage, 48 volt.
Actually, it's similar as we talked before, right? It's a 50 to 48.5.
Yeah, I just want to mention because the Open Rack V3, we actually try to adjust the voltage to work with the battery. And the voltage of the power system, we set it 51 to 50 and the battery 48 to 47. It would be great if you guys can do the similar thing. I know you don't have the battery, that you don't be worried.
Yes.
But if you set your voltage very the same as what is on Open Rack V3, which is 51 to 50, that makes this solution works with for Open Rack application and and for the rest of the Open Rack, for the rest of the system and rest of the industry, and especially when they use battery.
Yeah, I will consider that.
Yeah, that would be great. Let me go to see. I think we are out of time. Sorry.
Okay.
Yeah.
Okay. Thank you.
Yeah, I think there are a few questions